Today I'd like to share a project that I've been working on. It's a code practice oscillator. Now I expect some are saying, "I'm beyond that, show me something interesting." Well, possibly true, but maybe you know someone who isn't. And a variant of this theme may be just the thing that opens a whole new world to them. So let's press on and let's see if there's a nugget in here. Now, Arduinos are popular building blocks in the maker world, and given earlier work done with them, they seem like a good fit for this effort too. In fact, let's start by taking a look at the $4.50 micro and look at what else is needed to make a functional code practice oscillator. Turns out, if you have a key and a 5-volt source, one resistor and a speaker is all that's needed. Take a look as I play with this minimal configuration, and yes, I know there are 200 ohm resistors here, but effectively they are in series, so 200 ohms or 180 or 120 ohm resistor will work just as well. Their purpose is to limit the output current to 20 milliamps, which is the max that the individual I/O pins are spec'd to source or sink, but still plenty enough to excite the speaker. With a loaded sketch, this SS Micro has 3 input pins. Digital pins 10 and 11, when grounded, act as DIT and DAW pins for a paddle input, and on the other side, digital pin 16 will accept a straight key input. Now you could stop right here, hook up your key or paddle, and have a perfectly usable code practice oscillator. But if time permits, and battery power is desired, then you could add an LM2596 breakout board and have a standalone code practice oscillator that will run on any DC source from 3 to 30 volts. Here I'm using a 9-volt battery as the source and can report that a good 9-volt battery lasts for a long time. I got 5 of these for less than $8, so to my thinking, the less than $2 increase in project costs was well worth the investment. And by using the breakout board, it's just 2 wires in and 2 wires out. Here I've added a 1/4-inch stereo phone jack, a couple of normally closed push buttons, a single pole single throw switch, and another 680 ohm resistor, which I'll explain later, to form my version of a standalone code practice oscillator. The switches and jack are mounted on a piece of angle aluminum, which is in turn attached to the wooden base with 3 small wood screws. At the far right of the base, I glued a 3/16 U-shaped piece of plywood to form a holder to keep the micro in place, and then used some headers and point-to-point wiring. Now bear with me while I connect the key to the oscillator. Again, we could stop right here and have a perfectly usable practice system. But suppose you're one of those folks that wants something more and needs to know, did I really send it right? What would it take to have a code practice unit that provided a little feedback. Well, if you have another Arduino handy, say like a Uno, or much better yet a Leonardo, the Leonardo can be had for under $5, and then add to that a $13 touchscreen shield like this one, then you have pretty much everything you need to do this. This is a Leonardo that I've attached 3 leads to. The gray wire is connected to ground, a red lead is connected to the plus 5-volt bus, and finally the white wire is attached to the Leonardo's digital pin 0 trace. I elected to attach them like you see here because the LCD shield, as you will see in a minute, covers their respective header pins, and I was comfortable doing it this way. But for sure, there are other ways to make these same connections, so use whatever method works best for you. Right here is where that 680 ohm resistor mentioned earlier is coming into play. It's connected to the micro's pin A2, which in this case is acting as a digital output that goes to ground synchronous with the generated tone. In other words, it could drive a transmitter's key input, but depending on the transmitter could require additional buffering because it's only a 5-volt signal going to ground. But here we're using it to drive the Leonardo's interrupt pin, so there's no problem. If you are using an Uno, then the interrupt pin is digital pin 2, which is a shared pin with the shield, and may be trying to source or sync 5 volts. So, hence the need for the 680 ohm resistor to limit current flow when there's a conflict in usage between the two devices. Also, there's nothing magical about the 680 ohm value, and although I haven't tested it, suspect anything between 470 ohms to 2.2K would probably work just as well. The important thing to understand here is, if you elect to implement this sketch with the Uno, there'll be times when the interrupt feature won't be available, and as a consequence, the Uno will fail to detect the key closure. So, from a construction cost perspective, it's a relatively trivial matter to add decoder functionality to our setup, allowing us to instantly confirm that we are sending readable code. In my book, that's pretty neat. Again, we could stop right here and have a perfectly usable practice system. But suppose you're one of those folks that wants something more. To me, given that we now have a decoder and our goal is to gain code proficiency, the next logical step is to come up with a method that allows us to listen to some real-world code conversations and find out what goes on in a typical QSO. Toward that end, if we could substitute the key input to the decoder with some kind of audio interface, then, in theory, we would be good to go. Well, being the guy who only has a hammer and every problem looks like a nail, this looked like something another Arduino could solve. So, getting out my favorite nail, a SS Micro, and then taking an Adafruit Max 9814 breakout board, I connected the two together as you see here. Namely, the 9814's audio out has been connected to the Micro's A0 analog in. Also connected is 5 volts, ground, and the gain pin. Then, to turn the audio from the 9814 into something usable, I turned to this sketch found here and adapted it to run on the Micro. The basic idea with this sketch is it uses a fast Fourier transform to convert the analog input into a frequency versus energy data stream. Another neat thing about this sketch and website is that it included a link to an external processing sketch that gives you a real-time visual of the data stream. Working from there, I added the code needed to select the frequency of interest and what energy levels represent a closed key condition. All this may seem a bit abstract, but here's a live view of the processing graphic when the 9814 is listening to a receiver with a 600 Hz filter tuned to an open segment on 40 meters, i.e. white noise. The bump in levels on the left side of the graph is the noise that the 600 Hz filter is allowing to pass. Bins 7 through 10 on the x-axis if this video lets you see that kind of detail. Now watch what happens on the left when the Morse code signal is present. Each time the tone is present, the FFT reports dramatic energy increases confined mostly to these 3 bins. Now let's turn our attention to the 4 bins on the right. For this video, these are not normal FFT bins, but instead represent the results of this sketch's post-processing. The inner bars represent threshold values, while the outer bars indicate whether the current signal is above or below threshold. The reason there are 2 is the one on the left is used to detect the key down or tone on event, and the pair on the right do just the opposite, and is used to detect the tone off event. So the key down event is signified by the left sidebar being above the threshold's marker, and the key up event is signified when the far right bar is below the threshold marker. Are you confused yet? If you are, don't worry about it. The processor has no trouble keeping up with it. Now let's move back into the time domain and watch the micro as it tries to track the incoming analog signal shown on the bottom trace and regenerate the key up or key down condition shown on the top trace. Okay, that looks pretty encouraging. So let's connect this output to our decoder and see what happens. Now might be a good time to explain what the values in the lower left-hand corner of the display represent. In the current mode, the 2 digits before the slash are reporting the apparent words per minute. This calculation is based on 1200 divided by the average DIT duration measured in milliseconds. So, a 100 millisecond DIT would be interpreted as 12 words a minute. The digits after the slash represent the DIT to DA ratio, and generally 3 is considered to be the ideal value. Touch this area of the display to change the report mode. When 3 sets of numbers are showing, you are seeing in milliseconds the DIT duration, the DA duration, and the space duration in that order. And in an ideal world, the first and last set of numbers would be the same, while the middle would be 3 times the value of either number. These values and their ratios govern how the decoder parses the data it receives into letters and words. Okay, I'll stop here. Thanks for watching. As always, I'd like to hear your thoughts on this topic, and if you try some of the concepts presented, please share your experience. Thanks and good luck with your next project.